Hi, I'm Kate Saenko from Boston University and the MIT IBM Watson AI Lab. And today I'd like to talk about dataset bias. So we know that supervised learning has been extremely successful for many applications, and it works well when we have access to a lot of labeled data and a lot of compute power. But we also see a problem of dataset bias, which happens when the training data that the model is trained with is somehow different from the test data that it's being asked to label at test time. This can lead to a large drop in performance and sometimes can happen in unexpected ways. We call this problem dataset bias or domain shift or distribution shift. So how can we tell if our dataset is biased? Well, we often notice when we test the model on a new dataset. For example, here we trained an object classification model on web data, and then we tested it on robot data, and we saw a large drop in performance. Another way we can tell is if we play this guess the dataset game, where just by looking at the distribution of images, we can actually guess which datasets they came from. So all of this indicates dataset bias. But it can happen even when the new dataset is collected in a very similar way to the original. So here, they train a model on the original ImageNet and then test it on a new ImageNet test set collected in the same way as before, but they still see a big drop in the accuracy. So this indicates that deep learning models do not generalize well even to seemingly small shifts in the distribution. So how can we tell if our data set is biased? Well, I would argue that if we have high dimensional data, which is very hard to sample IID from the true distribution of data in the world, then our data set sampled in a finite way, any finite sample data set will always be biased in some way. And so the real question is not, is it biased, but how is it biased and can we somehow deal with this problem? So let's see how many or what kinds of types of distribution shift we observe in practice. One of them is the one I mentioned, which is a change in the sampling strategy, or also a change in the background, the poses of the objects, the lighting, and so on. It could also be the sensor that's being used to collect the data, or an even larger shift can happen when we train in simulation and test on real data, or it can be a shift due to the geography or the demographics of the data, or even the culture of the images and where they're collected. So this is by no means an exhaustive list, and in real applications, we often have a factor or many factors that are mixed together, and we have a hard time estimating what kind of shift we'll actually observe. And by the way, dataset bias has some real-world implications. For example, researchers found that face recognition models are trained, often trained on data sets that are biased towards lighter faces and male faces. And then this is a big factor in their unfairness on darker faces and female faces. Another implication in the real world is if a data set is biased in such a way that it doesn't cover some rare situations. For example, if all the pedestrians in the training data happen to be in the crosswalk, and then at test time, if the model sees a pedestrian not in the crosswalk, it may not generalize, and this could cause a very serious failure. Okay, so you might be wondering, well, can't we just fix this by collecting more data? Well, I would argue that this would be very difficult to do in practice and very costly. So let's take an example of semantic segmentation. Here, if we wanted to label pedestrians, we could label around 1,000 polygons for about $1,000. So not too bad. But let's say we also want to cover different poses and different genders, which would increase our budget. And then if we also want to cover different age groups and racial groups, clothing styles, weather, the city, the time of day, and so on and so forth. So essentially, the labeling budget is going to grow exponentially if we want to cover all possible variations. And by the way, we also want to cover more rare events like, for example, people riding wheelchairs. So in this talk, the approach we'll take is instead, let's label the data we can label with our budget, and then let's collect some unlabeled data from new distributions. And now the problem becomes, how do we adapt the model from the training distributions to the test distribution? We call this problem domain adaptation. Let's define it more formally. So in domain adaptation, we have a source domain ds with a lot of labels, and then we have a target domain dt, which is unlabeled, and there's a difference in the distribution in the source and target data. So it's similar to semi-supervised learning, except for this difference in the distribution. And so our goal is to learn a classifier f that achieves a low loss on the target distribution. And we do assume that we get to see the target data, just not the labels. So why is this problem different? How is it different? Well, so one thing that causes poor performance with distribution shift is this difference in the training point distribution, which you can see here in blue, and the test distribution, which you see in red. And here, this is a t-SNE embedding where the red points are encoded using the classifier trained on the source points, on the blue points. So one idea is to fix this is maybe we can somehow align these distributions and reduce the difference between them. And indeed, so this is one approach that we can take, where let's say we have the source data with labels, and then we have some unlabeled target data. And so now we can add an unsupervised loss, which encourages some statistics of the distributions to be more similar. For example, the means of the distributions. So this is an approach that we call domain confusion, because the encoder is trying to confuse the two domains where their distributions become very similar. Another approach is to align both the mean and the correlations of the features. And by the way, we can apply these losses to any layer in the deep network, so any layer in the encoder. This is also similar to what we could do with batch normalization if we did it separately for each domain, because it also would normalize the means and the variances of the features in the activations of the layers across the domains. Okay, but what if our distributions are different in a more complex way? Can we do something stronger? And so this is the idea of adversarial domain alignment, where we're now going to add a separate network, which we call the domain discriminator. And the discriminator's job is to distinguish the two domains, while the encoder's job is to increase the error of the domain discriminator. So we train these two networks with an adversarial min-max objective. And so this approach has been quite successful. In fact, so here's an example of the different domain shifts that we can try for the 10-digit classification task. And you can see that when we train and test on different distributions, we see a very large drop in performance. But if we apply this adversarial alignment idea, we see that on the right-hand side, the red and blue points, the distributions of the source and target points, have been very well aligned. And then also, if we look at the accuracy of the classifier on the target test data, it also improves quite significantly. And so this is nice because we essentially are improving performance on our target distribution without any labels from the target distribution. So it's akin to unsupervised fine-tuning in some ways. Okay. But can we also apply this idea of adversarial alignment in the pixel space? In fact, yes, we can. So here we take the source data images, the raw images, and we use a conditional GAN to translate them into the target domain using the unlabeled target images. Okay, and then now we can take the translated source data with the labels and use it to train the encoder. And also we can still use the feature alignment loss. And this is what we did in our Cicada paper. And we showed that doing both techniques actually works better than just doing one of them. So let's see an example. So here we're translating images from our training domain, which is this synthetic domain from the Grand Theft Auto game, into our target domain, which is real data from the Cityscapes dataset. And you see that the pixel alignment makes the source training data have a general style of the real target data. We also see a big improvement in the pixel accuracy on the target domain. On the digit classification task, we also see that the pixel alignment is able to make the street view house numbers look like they are handwritten numbers to match this MNIST domain. And without pixel alignment, we still improve performance compared to training only on source. But when we also add feature alignment and pixel alignment, then we improve performance even further. So the takeaway here is that unsupervised image-to-image translation can help us by changing the image style to match the target domain. But what if we don't have a lot of unlabeled target data to work with? What if we only had a few images of the target domain? So for example, let's say that we have dogs in our training data in the source domain, and then we have new distributions with new breeds of dogs. But we also have one image of this new breed, or maybe a few. So we propose a method for this few-shot pixel space translation problem, which we call CocoFunit, which takes the source image and keeps the content. In this case, the content is the pose of the dog, but translates it to have the style of the target domain. So here the style is the breed of the dog. Okay, so what are some of the pros and cons of this pixel versus feature space alignment? What are the trade-offs here? So with pixel alignment, it's kind of easier to see what's going on because you can just look at the predicted images. But the downside is that you can run into problems that you see with GANs, for example, mode collapse, or if the translation is one-to-many, for example, there are multiple backgrounds possible in the target domain. So in these cases, these models tend to cheat sometimes. And so in general, this problem is very difficult to solve. On the other hand, with feature alignment, we don't have to have a generative model of everything in the target domain, but it can also fail in unexpected ways. For example, it's hard to tell just by looking at the loss if the adaptation is succeeding, and so it can sometimes diverge and fail silently. But nevertheless, these techniques have been quite successful for domain adaptation. Actually, there's another problem with distribution shift that I haven't mentioned yet. And that's this issue of the model trained on the source data not having enough discriminative features for the target test distribution. You can see that here where the red points are not as well clustered into categories as the blue training points are. So what can we do about this? Actually, the marginal distribution alignment technique that I've described so far doesn't handle this very well because it ignores task-specific decision boundaries. Right? The domain classifier doesn't care about our actual task. And so you can have this problem where after alignment, the target domain features can fall very close to the task-specific decision boundary. And so these features will be ambiguous and the model will misclassify them. So we can solve this by throwing away the domain discriminator and using our task classifier to do alignment. So we call this class conditional alignment. And so here the idea is to use the task classifier to push the target points away from the decision boundaries and closer to the source points. And so at the end, the hope is that the resulting feature space is more discriminative in the target and there aren't a lot of points in that ambiguous decision boundary area. We can do this in several ways. One way is to minimize the discrepancy of two classifiers where we first train two classifiers and then fix them, and then we minimize the discrepancy or disagreement of these classifiers on target points. So the two classifiers will have the highest disagreement on points that are nearest to the decision boundary. Another way is to optimize the entropy of the classifier. So here I have a single classifier, and we first maximize its entropy to align the two domains, and then we minimize the entropy to cluster the target points away from the decision space. Okay, so that's all great, but we're also still ignoring another problem that could happen, which is that we might have categories that are not shared between the source and target domains. So here, for example, we have some shared categories that happen in both source and target, but we might also have some categories that only exist in the source, and we might have some categories that only exist in the target. And it's hard to know that because if our target distribution is unlabeled, we might have no way of knowing that there may be some novel classes in that distribution. And actually, standard distribution alignment doesn't work well here because it will try to align parts of the distribution that shouldn't be aligned together because they're different categories. So we propose a method to solve this problem, which we call domain adaptation with neighborhood clustering, or DANCE. So the first thing we do here is we take, for any target point I, we compute its probability that I is a neighbor of another point j. And then we minimize the entropy of this distribution. So what this does is it pushes close neighbors of I even closer to it, but it pushes far away points even further away. So it encourages clusters to form without actually computing discrete clusters. So once we've optimized this loss on the target points, then we also want to push the unknown novel categories in the target further away from the source distribution. And we do this with an entropy separation loss. So this is similar to open set classification. And then finally, the hope is that we end up with a feature space where the shared categories are aligned between the two domains. But we also learn to reject unknown categories in the target domain as kind of novel classes, unknown classes. Okay, so let's see an example of this on the Office Home dataset. So here we have some shared classes. Blue are classes in the target, and red are the same shared classes but in the source. But we also have green points, which are classes that only happen in the source domain. And so what happens when we align standard adversarial adaptation, we end up with this bad scenario where a source-only class becomes aligned with something in the target. So these target examples will be misclassified. On the other hand, when we apply our dance method, we see that even after adaptation, we have a much better situation where the source-only green points, for the most parts, are not aligned with any of the target points. Okay, so far I've talked about using this idea of essentially in-domain self-supervision to train the model in the target domain. But what if we could also apply this same concept to cross-domain self-supervision? So here the idea is to find the nearest neighbors of a point, but in the other domain, and then minimize the distances between them. And so after doing both cross and in-domain self-supervision, we hope that we end up with a better aligned feature distribution, but we can do this without any labels whatsoever. So there are no labels in the source at all. So we can think of this as a pre-training stage, essentially, unsupervised pre-training. And then we take the weights and initialize our representation for downstream tasks that we want to do. So tasks that might involve having labels on the source, for example. Okay, so let's see an example of this applied to cross-domain retrieval. So here we have an input query image from domain A, and we want to find semantically matching images in domain B. And if we use standard ImageNet pre-training, we see that the matching images are similar more in the color of the background and the foreground than in semantics. But if we use our CDS pre-training, we get matches that are much more similar in semantics to the query. And then if we look at the feature distribution, so on the left, the features are color-coded by category, and on the right, they're color-coded by domain. We see that with standard ImageNet pre-training, there's a large gap in the two distributions. And then if we do standard in-domain self-supervised learning with instance discrimination plus apply a domain classifier, we see that the picture is not much better. But on the other hand, with our cross-domain self-supervised pre-training, we see that the two distributions become much better aligned, and that the features are also discriminative for the categories. We can also apply this idea to the downstream task of universal domain adaptation. So here the H-score measures how well we're rejecting novel classes. And we see that compared to existing methods, the ones that are not designed for open set do not improve much, like DANN does not improve because it's a closed set method, essentially. But the other ones do improve performance. And then when we compare this to our dance method, it improves the class accuracy, but not the H-score. But if we apply this pre-training idea first and then apply dance, we see an improvement in both H-score and class accuracy. Okay, so this idea of learning domain invariant features is actually related to the idea of feature disentanglement. So here we want to represent images by learning a feature space that's disentangled into the class-specific features, like, for example, the shape of the strawberry or some object parts like the seeds, and also some other features which are specific to the domain, like the distribution over colors or contrast or the viewpoint, for example. And so we propose a method like this that takes several domains, some of which could be labeled, and it learns to generate features and then disentangle them into the red domain-specific part and the blue category-specific part, where the category-specific part is used to solve the actual task, to classify the image, but the red part is used to classify the domain. And so there's also adversarial loss applied across the two streams. And then to make sure that we don't lose information, we reconstruct the original feature vector. So this blue path is essentially the same idea that I talked about before, where we can now keep these domain invariant features for the actual task that we want to solve. But what about these domain-specific features? So these features will encode something about that domain, for example, the style of the domain, like the color distribution, viewpoint, and so on. So we can use these actually to measure distances between domains. So let's say we have a new data set, and we want to find what other data sets are similar to this data set visually. And so even if we don't have labels, we can try to find other data sets by mapping each data set using this, what we call domain tovec embedding. So this embedding learns a feature, a vector representation of a whole domain by extracting features that are specific to that domain via this disentanglement technique that I just talked about. And then we can find other data sets that are similar in this embedded feature space, or data sets that are further away in this embedding. And so the way this works is we concatenate the average domain invariant feature plus the diagonals of its gram matrix. And so we can take a bunch of different data sets and use domain tovec to map them to this graph where the nodes, each node is a data set and the edges represent similar data sets, similar domains. For example, here we see that there's several face domains that get mapped close together, but far away from, for example, sketches or logos. Okay, so speaking of data sets, one of the difficulty in doing research in dataset bias is that we don't have that many data sets with multiple distributions. Usually, data sets are collected and then sampled IID to create the training and test sets. So we had collected a data set called Office 31, which had become a sort of first standard benchmark in this field and has been used by lots of different methods over the years to improve performance, and at this point has more or less saturated in performance, so we're doing quite well on this data set. And so we also collected a larger data set that we called VISDA, which has also a more difficult shift from simulated images to real images. And so now we've held a few competitions on this data set, and we also see that on the closed set adaptation task, we are starting to reach very high performance, close to the 90s. But it's still challenging for open set or universal domain adaptation. But also this data set only had 12 categories. So we have recently collected an even larger data set called DomainNet, which has something like 350 different object categories and 0.6 million images total, split across 6 different visual domains. So this remains a very challenging benchmark, and we hope that it leads to further improvements in this research area. Excuse me. So to summarize what I talked about today, I started with this question, is my data set biased? And hopefully I've convinced you that chances are likely, yes, our data sets are always biased in some way. And I talked about how we can try to deal with this issue. If we have access to unlabeled data, then we can perform domain adaptation or transfer knowledge from the labeled distribution to the unlabeled distribution. And I call this some kind of unsupervised fine-tuning. But in terms of techniques, what I talked about is adversarial domain alignment, both in pixel space and in feature space, which can work quite well in the closed set setting. But with disjoint categories, what I've showed is that it can fail, but maybe we could use self-supervised learning, which seems to be key in overcoming this change in the categories between the source and target distributions. And then I also described how we can disentangle features into sort of domain style versus domain content, and then use the style part to measure similarities between different domains. But there are also lots of open questions here that I haven't even touched on, and also ones where there's less research. So for example, one question is how much distribution shift is too much, right? So how can we tell when we're still close to our original source data and we can try to transfer that knowledge, or on the other hand, maybe we have diverged so much that there's really nothing to transfer anymore, and the problem has changed in the data that we're receiving. So that's one open question. Another really big problem is how do we tune hyperparameters since we don't have any labels in our new target distribution? Another question is, can we generalize to novel data without any access to target domain data? So we call this domain generalization. Or a related problem is, how can we adapt at test time when we only get a small batch of target examples? So we don't wait until we see an entire data set of unlabeled target examples. So these are all very interesting questions, and there's some great work that's happening recently that's trying to address all of these questions. And so I want to finish the talk by saying thank you to my sponsors and also to my colleagues at the MIT IBM Watson AI Lab. And I want to thank my graduate students who, both current graduate students and former students, who've done all of the excellent work that I've talked about today. And I'd like to also thank you all for your attention, and I'll be very happy to answer any questions that you might have.
Hi, welcome everyone. I'm Solon Barocas. I'll be serving as the moderator of this keynote session. I'm a researcher at Microsoft Research and a faculty member at Cornell University. I work on policy and ethical issues of machine learning with a particular focus on fairness and accountability. And I'm very pleased to be able to introduce you to Kate Saenko, one of today's keynote speakers who you just heard from. You're very likely familiar with her excellent and important work, but I'll tell you a bit more about her. She is an associate professor of computer science at Boston University and a consulting professor at the MIT IBM Watson AI Lab. She received a PhD from MIT and was a postdoc at UC Berkeley and Harvard. Her research is on representation learning for visual and language data with a focus on generalizable, explainable, data efficient, and power efficient models. You just heard her talk today about is my data set biased? And as we all learned, the answer is likely yes. We also learned why that is, what the consequences of that might be, and what we could possibly do about it. So student volunteers and I have been monitoring the questions that have been coming in through Rocket Chat. I will draw on these questions in this Q&A, but please continue to ask questions. We'll continue to monitor it as we go. And we have a good amount of time for this Q&A, a little under 30 minutes. So maybe what I'll do is actually just start with a very basic, almost fundamental question here before turning to things that are a little bit more specific. So given the focus of today's talk, I'm curious if it even makes sense to ask the question along the following lines, which is, what would it mean to have an unbiased data set in the case of computer vision? Is that even a meaningful question in the case of computer vision?
Yeah, thanks a lot, Solon, for that question. I think when I named my talk, "Is my data set biased?" it was a little bit tongue-in-cheek because, at least as far as I think about it, the way I think about it, when you have complex high-dimensional data, such as images, or it could be text, or it could be another modality. But if you have a very highly complex data that's very real world and complex, and you're trying to sample a representative data set, it's very, very difficult to kind of have equal coverage of all possible variations. So, and then you also have natural distribution variation across different attributes of your data. So for example, if it's people, you will have different attributes of those people that just are prevalent at different rates in the natural distribution in the world. So then you would have to actually correct for these differences in frequencies across different attributes, such as ethnicity and then skin color and all of these kinds of attributes. So but then there's also things that are hard to anticipate. Some latent factors that we as humans, or maybe as users of machine learning, just people who have a problem they want to solve, it's hard for them to anticipate that there is something in the data, some latent factor variation. Maybe it's just something related to the timestamp somewhere, or something else that isn't quite covered in the data set. Because our data set collection is very expensive, very time consuming, as we all know. So inevitably, when we collect data sets, we take shortcuts. We use the cheaper way of collecting it. We want to save money. We want to save resources. We want to save time. We'll scrape data from the web because that's where it's available and free, or for the most part free, as opposed to hiring people to go out and take pictures for us, for example. So all of this results in biases in practice. And, I think for that reason, it's really what I'm trying to say in my talk is that all of our data sets are biased. at least for computer vision, I think I can say that with confidence.
Thanks, Kate. Maybe I'll go now to some questions that have come in from the audience. And I think another maybe kind of foundational question here is that, are some of the techniques that you review in the talk applicable outside the context of specifically deep learning and computer vision?
Yeah, so some of these techniques are very generic. Certainly anywhere that you can apply deep learning, I think these techniques can be applied. I think, you know, for example, distribution alignment. This is something that has been applied to textual data. Not just images or videos, not just visual data. In fact, we've used some form of distribution alignment in our work, in my group, when we look at, for example, classifying documents, classifying text documents. And you know, in textual domains, you could have data set bias as well. For example, something that's I've come across recently because I have a project on detecting fake neural news, so news generated by neural networks, and in general, just analyzing, you know, analyzing news data in the news domain. You'll have a domain bias when your news training data set, for example, comes from particular news sources, say the New York Times or the Washington Post, would be more left-leaning, for example, bias, and maybe not covering something else. Or you know, at test time, you might get news coming from different sources, like you know, more right-leaning or even more blog oriented kinds of news. So there's always some source of bias, and I think there we've also applied these similar techniques. You know, I think in robotics, you know, it's kind of more related to computer vision maybe, but you know, in depth, kind of depth measurements or other sensors that collect high dimensional data, you can also apply some of the same techniques.
Thanks. And actually, in the process of answering this question, you answered another question, which was going to be about NLP. I'm going to maybe try to paraphrase a question here, which is to kind of just ask a little bit more about the challenges of collecting some of these data sets with the goal of kind of having different distributions where we can learn maybe in unlabeled different distributions. So in watching the talk myself, I was thinking, you know, how do we know that this kind of other domain that we're sampling from has the specific different kinds of distributions we care about if the data is unlabeled? And of course, I think the answer is somewhat easy in the case where we're going to apply it specifically to that domain. But what if we're doing this in the hope of being robust across domains? And so that was a question that at least stood out to me.
Yeah, that's a great question. In my talk, and sort of just as a function of the work that we've been doing so far, I focused on this case where you have a specific deployment domain. So you know, you have your training data, and now you just have your model kind of out there in the real world, you know, receiving real life data, and you're able to collect unlabeled data from this target distribution that you're really targeting. And you know, so some examples might be, you know, you had collected some data and you were able to get a lot more data from web domains, for example, because they were cheaper, and you labeled a lot more of them. But then at test time, you have people taking pictures with their phone in their homes, and that data, you know, is kind of more difficult to collect but you know, and label, but you can train on it in an unlabeled way. So yeah, I think that's an easier case. But the case you brought up, exactly, you know, you may not be able to collect unlabeled data from your final target domain. And also, you may want to anticipate and actually handle future domain shift without needing unlabeled data from those domains. if you really have some sort of high stakes, application, you don't want to kind of wait until you get some unlabeled data and then go back and retrain your model. You want it to work immediately, even on, handle any kind of new shift. And I think that's a much harder problem. It's technically, the term we use in the community is domain generalization. So as opposed to domain adaptation, where you have some unlabeled data from your target domain. In generalization, you might be given some domains at training time, but at test time, you don't get to see any data from your input test distribution. And that becomes much harder, and basically involves, I think the solution there will be to design methods that can learn from as much of a variety of distributions as you can have at training time, and kind of learn to generalize to completely new data. But that's a much harder problem.
Thanks. Maybe something again along these lines is a slightly different setting. So a question here is about what are the kind of points to consider when doing domain adaptation for time series data? So where but the setting is slightly different.
Right. So I think that in time series data, you could still apply a lot of these techniques. Actually, one of the interesting aspects of time series data is that your domain might be changing as a function of time. So this is something that my co-authors, including Judy Hoffman, who's now Georgia Tech. So we've looked at this a while back, where your domain is sort of a function of time, and it's changing continuously. So instead of having a fixed distribution at test time, instead of having a fixed target domain, you actually have a dynamic distribution over the input that keeps changing. So one example of this is if you put a camera, a surveillance camera somewhere, and it's receiving images, and over time, the time of day changes, or maybe the seasons change. You might get some snow or some rain sometimes, or windy conditions and so on. So that's just one example. But in any time series domain, you could have this case of, okay, so it's not actually one fixed domain. There are continuously changing distributions, and you could actually design methods to specifically adapt in this setting as well. There's some great work. I've seen some papers recently pop up, including, I think, in CVPR this year and other conferences, where people are looking at this problem and trying to say, okay, if you have these continuously changing domains, maybe as a function of time or something else, can you design a method that can adapt kind of in an online fashion, essentially?
Thanks. So I'm going to try to ask some more technical questions, and I may just read them directly to make sure I don't misrepresent them. And this, I think, maybe circles back a little bit to a question earlier. So in the case of unseen categories in the target, are the two distributions still of the same form and differ only in parameters, or different kinds of distributions altogether?
Sorry, do you mind repeating the question?
Sure. And in fact, I'm asking it literally to make sure I don't misrepresent it. So the question is, in the case of unseen categories in the target, are the two distributions still of the same form and differ only in parameters, or different kinds of distributions altogether?
So I think if I understand the question correctly, it's asking what happens if you have unseen categories at test time. So categories that are not part of your training data set, not part of your source domain. I think so in distribution shift, we can think of different distributions. You can think of the distribution over the input, so P of X, and P of Y, distribution over the labels. And when we get different labels at test time, that P of Y is changing. So the distribution over the labels is different compared to the source domain. But also P of X is also changing. I mean, it's still, you can still think of it as the distribution over the inputs, but at training time, those inputs included or did not include certain categories, and at test time, they do include certain categories, but P of X essentially is what we're thinking of here. And we can directly compare, you know, P of X in the source and P of X in the target. So yeah, I think hopefully that answers the question, if I interpreted it correctly.
Great, thanks. Let me maybe ask one more kind of question about how much what you've surveyed in the talk might apply to other settings. So the question here is about, is it possible to use these techniques in a regression framework as opposed to a classification one? And how about with multitask learning?
Right, so that's a good question. So with regression, I think it still should be possible because you sort of have the feature encoder part of your network, which is learning, you know, that's the bulk of the learning that's going on. It's learning the representation. It's learning, you know, this layered hierarchical feature representation from the raw data. And it's, of course, it's learning that through the final task, be it classification or regression. But my point is that we can apply the sort of some of these techniques, such as distribution alignment, to that representation part. So basically, any layer that's not the final task layer, not the final layer of the network, we can apply those losses there. Or, you know, if we're doing pixel domain alignment, or basically alignment at the raw data space level. So be it pixels, or be it maybe words, or some other data that you're working with. You can also do that for any, you know, regardless of the task that you have, classification, regression. But when we get into some of the other methods that I talked about, maybe ones, you know, that specifically deal with novel categories, I think that's not as applicable to regression tasks because, you know, we don't have the notion of categories in regression. And also the method that I talked about, which uses the task classifier itself to try to align the distribution so that the distribution alignment process respects the task boundaries, so the decision boundaries between the classes we care about. That method doesn't directly apply to regression, but you know, it probably could be extended to regression. We just we have some regression problems that we've worked on primarily in the object detection realm. So where, in addition to classifying the object category, you also want to perform a regression on the bounding box coordinates of the object. You know, I think that's an interesting area also where we can think more about distributional shift specifically for regression problems. I don't see as many papers on that as on classification. And I think the other question was multitask. I think it depends on how you define tasks. So I think if it's multi-label, I think that could be incorporated. You know, in some ways you can think of different distributions as different tasks. You know, people define tasks very differently depending on who you talk to. So yeah, I'd have to kind of know a little bit more about the nature of the problem.
Thanks, Kate. That's very helpful. I'm going to ask a kind of more open-ended and forward-looking question now. So someone that sort of expressed curiosity about moving some of these approaches into practice and is interested in where you see particular promise for moving these techniques into practice, and also what are some of the challenges that you think might need to be overcome in order to move this into practice?
Yeah, that's a very good question. I think that in some ways, domain shift and dataset bias are extremely highly practical problems that occur all the time in practice. But at the same time, I don't see kind of as much of an adoption yet. I think it's still maybe a research problem, but hasn't been fully adopted into practical applications. And it's, you know, it's possible that one of the reasons is that it's an unsupervised or semi-supervised learning problem. Essentially, you're learning on unlabeled data, and that comes with challenges. Specifically, how do you set the hyperparameters of your model if you don't have any labeled examples, or at least not from your target domain? And as we all know, deep learning models have lots of knobs to tune, lots of hyperparameters to set. And you know, there's really we can't really avoid that in practical applications. So I think that's one of the challenges still, that for any model that is working on an unlabeled data set, just learning from essentially we're learning from the unlabeled target distribution. We can't really, we don't really have a good way of setting our hyperparameters. We have some work on that recently in my lab, where we're trying to come up with unsupervised metrics that measure the quality of the representation and can be used to guide hyperparameter tuning. So basically unlabeled hyperparameter tuning for these methods. It seemed to work quite well in academic benchmarks. But I think that's one of the barriers that we need to overcome probably before these methods are widely adopted.
Thanks. I'm sure people will be very interested in that work that you mentioned as well. I may take the prerogative of asking a question that's a little closer to my research interest for a moment. We only have about 8 minutes left, and so I'll make sure to also leave some time to wrap up. But my question is, you kind of allude to the fact that a lot of the fairness concerns that have come up over the past few years of machine learning can be thought of as distribution shift problems and characterize even some of the work in that way. Is it fair to think, forgive the use of word, is it appropriate to kind of think of all fairness problems as distribution shift problems?
Right. Yeah, so there are definitely, there's a lot of synergy between dataset bias and distribution shift and fairness problems. I don't think it's fair to say that they're the same. I think some of the techniques are very applicable to both kinds of problems. But I think that in fairness, we often, and correct me if I'm wrong, because it's not really my primary research area, but we often have some attributes of our data that we care about. We care that those attributes are, we're following some equal error rate or some other criterion where we're fair across those attributes of the input data. And we have that information at training time. And also we sometimes don't just care about improving accuracy on one attribute of the data, but we care more about kind of more equalizing the errors or kind of having some criteria of fairness. And so there are all those differences that don't so much matter in domain adaptation. But I think there's a lot of overlap because, for example, if your data set doesn't represent certain categories of or attributes that you care about and want to be fair to, then a test time you do have them in the test distribution, that could be seen as a domain adaptation problem. But also, I would caution, I think whenever you have really questions of people, or you're making decisions about people or based on some data that you collect from people, be it images or video or some other data, I think that it really has to be approached with a much more nuanced approach, and not just kind of thought of as, okay, well, we'll just collect some unlabeled data and we'll add some losses and we'll see if we can just get better performance. But I think you need to really evaluate then what's happening, because in the approaches I talked about, you sort of have a target distribution that is not labeled and you don't really know what's going on there. But I think when you're dealing with people, it's very important to actually know what's going on in your target distribution. Maybe it has to be a much more hands-on kind of like, you need to spend resources on labeling as much as you can along the axes that you care about.
Thanks, Kate. I really appreciate that answer. We have about 5 minutes left, and though there are definitely additional questions I can ask, I also want to make sure I give you a moment to mention some things that you're particularly excited about in general for the future, including possibly this workshop and competition that you're organizing.
Yeah, thanks for that. I did want to mention that we're very excited that we are going to have a competition at NeurIPS 2021, so the upcoming NeurIPS conference. And it's going to be on visual domain adaptation. So we've been running a visual domain adaptation competition for quite a few years. It's called VISDA, V-I-S-D-A. So we've had successful competitions in the past that were co-located with computer vision conferences. And this is the first year that we're going to co-locate with a machine learning conference with NeurIPS. So we're very excited about that. And the specific focus of this year's competition is actually going to be on universal domain adaptation, which is what I talked about in my talk today, where you have some unknown overlap in the categories between your training distribution and your target test distribution. So I encourage everyone who's interested in this problem to keep an eye out. I think the competitions will be announced very soon, and then we'll have the website set up and you'll be able to participate. So yeah, so that's one thing I wanted to mention. I guess the other thing I'll just say is, I think it's very interesting to me, at least, this intersection between open set problems and domain shift problems, and also between domain shift and fairness and ethic problems. This is kind of where I would love to keep going in the future. And also thinking about it more in terms of how can we learn from unlabeled data. I think there's been a very strong trend towards unsupervised or really self-supervised learning in the machine learning community. But we haven't thought that much about doing it with multiple different domains or different shifts. I think that's kind of where I'm interested in going in the future, and we have some initial work in that direction. And also this problem of generalization, I think it's a very practical problem where you don't have labeled data from your target domain. So I think that's another thing that I'm very interested in. And, if anyone is curious to chat with me more, feel free to reach out to me. And also I'll check back on the Rocket chat and see if there's anything else that, any other discussion to have there.
Well, thank you so much, Kate. I really appreciate you fielding all these questions. I thought it was a wonderful talk, and I really enjoyed hearing all your thoughts to these questions. It's very generous of you to volunteer to take a look at the Rocket Chat questions. I'm sorry that I wasn't able to get to all of them, but hopefully you'll have a chance to interact with people further. So thank you again, and thank you also to all the people who watched and posed questions.
Thank you so much for moderating.